A kitchen sponge can hold several times its own weight in water. It sits beside the sink, gets squeezed every day, and is replaced often. Inside a factory, that walk begins as wood pulp, salt crystals, fibers, resin, and rough scrubbing material. In one shift, a line can turn those materials into thousands of packed sponges. The process starts with cellulose, the soft absorbent material used in many kitchen sponges. The cellulose usually comes from wood pulp, delivered to the factory as dry sheets or heavy bales. Forklifts move the bales from storage to preparation. Workers cut off straps, remove the wrapping, and feed the pulp into shredding machines. Inside, rotating blades tear the sheets into small flakes. Smaller pieces soak faster and mix more evenly. The shredded pulp moves into large stainless steel tanks, filled with water and sodium hydroxide solution. Slow paddles turn through the tank, keeping the pulp moving while the fibers swell and soften. This can take several hours. Sensors watch temperature, liquid level, and mixture thickness. Operators test how the pulp flows. If it is too thick, pumps struggle to move it through pipes. If it's too thin, the sponge can come out weak and flat. After soaking, the softened pulp is pressed to remove extra liquid. Heavy rollers squeeze it into a damp mass. Then crumbling machines break it apart again. In many cellulose sponge factories, the pulp is processed into viscose, a thick liquid form of cellulose. The treated pulp is dissolved into a smooth, heavy solution, because some chemicals used here need careful handling. This area has ventilation, gas sensors, and closed pipes. Workers wear gloves, face protection, and chemical-resistant clothing. Once the cellulose solution is ready, the factory adds the ingredient that creates the sponge holes, salt crystals. These crystals are not for cleaning. They are temporary space makers. Automatic feeders measure them into the cellulose mixture. Their size controls pore size. Fine crystals create a tighter sponge. Larger crystals create a softer sponge. Many factories use a blend, so the sponge holds water and springs back after squeezing. Short, reinforcing fibers are added next. These may be cotton, flax, or other plant fibers cut into small pieces. They help the sponge resist tearing when it is twisted or rubbed. Pigments are also mixed in, giving the sponge its yellow, blue, orange, or pink color. It enters a kneading mixture with strong rotating arms that fold the paste over and over. The mixer spreads salt, fibers, color, and cellulose evenly, because one poorly mixed area can tear during cutting or fail later in use. The finished paste moves to molding. Some factories pour it into molds. Others spread it onto a moving belt as a slab. A dosing system controls the exact amount of paste entering each mold. Too little material makes a thin block. Too much causes overflow and waste. Vibrating tables shake the molds gently, settling the mixture and removing trapped air pockets. Random bubbles create weak spots, so vibration helps the block form with controlled pores. The filled molds enter a heating chamber. Steam or hot water raises the temperature to about 90 to 100 degrees Celsius. Under heat, the cellulose turns from paste into a solid sponge network. The salt crystals stay trapped inside. Timing depends on thickness. A thin slab may set it less than an hour, while thicker molds may need several hours for heat to reach the center. Probes check the chamber and mold surface. If the outside curves while the center stays soft, the block can collapse or shrink unevenly. When the blocks leave the heater, they are warm, heavy, and full of salt. They also contain leftover processing chemicals, so they cannot be packed yet. The blocks move into a washing line with tanks, conveyors, and squeeze rollers. Warm water flows through the tanks. Rollers press each sponge block flat, pushing salty water out. Then the sponge expands and pulls clean water in. This repeats many times. As the salt dissolves, it leaves behind the connected holes that make the sponge absorbent. The wash water is tested. Conductivity meters measure how much dissolved salt is still leaving the sponge. High readings mean more rinsing is needed. Low readings show that most salt has been removed. The water may also be checked for pH to confirm that chemical residues are leaving the sponge. Workers squeeze samples, smell them, and check texture. A clean block should feel flexible, have even color, and show no hard lumps. Blocks with odor, streaks, brittle edges, or dense patches are removed. After washing, the sponge is clean but soaked. The blocks pass through compression rollers that remove water without crushing the pore structure. Then they enter a drying tunnel. Warm air moves around the blocks while fans carry moisture away. Drying temperatures may sit around 70 to 90 degrees Celsius. The target is controlled moisture, not a stiff, dry brick. If it dries too fast, it can shrink. If it stays too wet, it is hard to cut and bond. Dried blocks move to slicing machines. Band knives, sharp wires, or horizontal blades cut each block into sheets. Conveyors feed the material forward at a steady speed, while guides hold it flat. Optical sensors check thickness as the sheets leave the blade. A common sponge layer may be about 20 to 30 millimeters thick before final compression. Operators check samples with calipers to catch blade drift. Trimmed edges and scrap pieces are collected by vacuum systems and separated from good material. For plain sponges, the process could go straight to final cutting. But most kitchen sponges have a rough scrubbing layer, and that layer is made of another line. It starts with synthetic fibers such as nylon or polyester. Fiber bales are opened in a bale breaker and fed into a carding machine. The carding machine combs the fibers into a loose web. A cross-laying machine folds the web back and forth to build thickness. At this point, the material is soft and airy, but it cannot scrub yet. To make it abrasive, the web passes through a coating area. Resin is sprayed or rolled onto the fibers, then abrasive particles are added. These particles may be aluminum oxide, silicon carbide, or softer materials. A heavy-duty green pad uses harder grit. A blue non-scratch pad uses gentler grit for coated cookware. The coated web moves through an oven at about 150 to 200 degrees Celsius. Heat cures the resin, locking fibers and grit together. Conveyor speed controls oven time. Too little time leaves resin sticky. Too much heat makes the pad brittle. After cooling, cameras inspect the scrub material for holes, thin spots, uneven resin, and poor grit coverage. Samples are rubbed against test surfaces to check cleaning power and scratch level. The pad must remove stuck food and survive water, soap, squeezing, and rubbing. Rolls of sheets that pass inspection move to the lamination line. Now the soft sponge sheet and scrub sheet are joined. The cellulose sponge travels on a conveyor while the scrub material feeds from above. A roller coaster spray system lays down a controlled amount of adhesive. Some factories use bonding film instead of liquid glue. The layers pass through heated compression rollers. The rollers press them together evenly, helping adhesive grip both layers. Pressure must be balanced. Too light and the scrub pad peels off. Too heavy and the sponge gets crushed. The laminated sheets rest while the bond cures. Quality workers pull sample strips and perform peel tests, separating the layers by hand or with a small testing machine. If the scrub pad lifts too easily, the line is adjusted. Adhesive amount, pressure, temperature, and moisture all affect bond strength. The bonded sheets move into final cutting. Rotary knives, die cutters, or guillotine blades divide them into individual rectangles. A common sponge may be around 100 millimeters long and 70 millimeters wide. Scrap strips are vacuumed into collection bins. The finished pieces continue in rows on narrow conveyors. Before packing, every batch goes through checks. Cameras look for missing corners, crooked scrub pads, color problems, and uneven cuts. Thickness gauges measure the sponge body. Check weighers catch pieces that are too dense, too small, or still too wet. Samples are weighed dry, soaked in water, drained briefly, then weighed again to measure absorbency. Other samples are squeezed in compression testers to see whether they bounce back or crack. Scrub samples are rubbed over standard dirty panels to measure cleaning strength and wear. Approved sponges move into packaging. Automatic counters group them into single packs. 2 packs, 4 packs, or larger value packs. Pick and place arms stack them in the correct direction. Flow wrapping machines seal the group in printed plastic film, while other lines use bags or cardboard-backed packs. Heat sealing jaws close the package at control temperature and pressure. Printers add batch codes, dates, and tracking marks. Packed sponges are loaded into cartons by case packing machines. Cartons are weighed, taped, labeled, and stacked onto pallets. A stretch wrapper spins firm around the pallet so the boxes stay stable in transport. Scanners report the batch and destination. Forklifts move the pallets into storage or onto trucks. The finished kitchen sponge looks simple, but it is the result of a controlled factory chain. Wood pulp is softened, chemically processed, mixed with salt, molded, heated, washed, dried, sliced, bonded, cut, tested, packed, and shipped. Every tiny pore comes from a crystal that was washed away. Every rough scrubbing face comes from coated fibers cured in an oven. Every sponge beside a sink has passed through machines built to turn plant fibers and grit into a common cleaning tool.